Hey folks, this is the third of 3 lessons on energy, 2 previous ones on kinetic energy and potential energy. In this one, I'm going to talk about energy conversions from kinetic to potential and the reverse, do some calculations with that, and we'll also talk about efficiency and do some calculations for efficiency. So we're taking a look at, of course, the data booklet here. So once again, we're going to need these equations here for potential energy and kinetic energy. Potential mgh, kinetic 1/2 mv squared. We'll be using those for our energy conversions. And the other one for efficiency, it's in a different location on your data sheet, kind of the opposite corner here. And we see it, formulas and data. This one here, percent efficiency, output divided by input times 100. So what we'll see is it's going to be in energy, output joules, input joules. They cancel out times 100%, and we convert it into the units that we want, which is percent efficiency. So that's what we will be using for your data sheet. I thought what I would do first of all here, although I'm not going to talk in detail about this, all kinds of energy transformations that are taking place, whether it's in a vehicle or whether it's in an electrical generating station. All kinds of different electrical generating stations. There are nuclear, there's hydroelectric, there's wind turbine, there's even solar generated, of course. Many different ones do use fossil fuels, so coal, natural gas, oil. This one here is a picture that does show using the chemical potential energy in coal. So what are all of the energy transformations? Well, eventually what we want to produce is electrical energy. So that's why they're showing these transmission lines here. Electrical energy that you use to, turn on the lights in your house and the dishwasher and the TV and charge your cell phone, all of that. So how do we get from chemical potential energy in coal to electrical energy? Well, a whole bunch of energy transformations. So we take that coal and we burn it, combustion reaction, and that converts the chemical energy into thermal energy. So that thermal energy is then used to heat water, high pressure steam, that's going to be passing through these pipes. So now it's kinetic energy. Okay, so chemical energy to thermal energy to kinetic energy because the steam is being forced through this plumbing. And then what it's going to do is turn a turbine. That's now mechanical energy. The turning of that turbine is connected to an electrical generator, which converts it to electrical energy. So these are all energy transformations that are taking place. In this case, from chemical eventually to electrical potential energy, which again can be used for various different kinds of work. So the energy conversions that we're going to focus on and that you're going to have to do calculations for involve potential energy and kinetic energy. And of course, we've done calculations with both of those already. Laws of thermodynamics are going to come into play here. So the first law of thermodynamics, this is what it says, remember, energy cannot be created or destroyed. It can only be converted or transformed from one form to another. So that coal energy that goes into an electrical generating station, the amount of energy in the coal that goes in at the beginning has to be equal to the amount of energy at the end. Unfortunately, it's not all electrical energy because a lot of it is released along the way in the form of heat. But the amount of original energy has to be equal to the heat energy and the electrical energy at the end, because energy cannot be destroyed and it cannot be created. So yes, we're going to focus on kinetic and potential energy. We already know that potential energy is energy due to position or condition, and kinetic energy is the energy of motion or movement. Those are the only two kinds of energy. We can put a whole bunch of things into kinetic, a whole bunch of things into potential, but ultimately at the end, these two here, kinetic energy and potential energy, will be the total energy. I think I have this on another slide, but total energy is the kinetic energy, I'll write it here as KE, plus the potential energy. So in this picture here, what it does show is way at the left-hand side, the beginning of this graph, what we have is 100% all potential energy. Gravitational potential energy is the one that we're going to talk about. And we have 0% kinetic energy. And then what's going to happen is some of that potential energy is slowly going to go down, but it can't disappear. Whatever is lost in terms of potential has to be gained in terms of kinetic energy. So again, if you take a look at this top line here, that is the total energy. That does not change. So here, 0% kinetic, 100% potential adds up to 100. Right here, it might be 50% kinetic and 50% potential. But again, it adds up to 100. It always has to add up to the total amount of energy. This here, from the top to the bottom, cannot change. Energy cannot be created and cannot be destroyed. So why does it kind of show this way? Well, it's kind of related to this pendulum that it has on the right-hand side here. So if we're initially holding up this ball at a certain height above the ground, if we're holding it in that position and it's not moving, there is 0 kinetic energy. It's not moving, but it does want to move. It wants to be pulled down by gravity. So what we have is potential energy, and specifically gravitational potential energy. So if you do release that ball, what's going to happen is the potential energy is going to go down, and the amount of kinetic energy is going to go up until it reaches right at the bottom. So when it reaches the bottom of the swing here, we're going to have, as it says, maximum kinetic energy. It's now moving and we have 100% kinetic energy. This is as low down as the ball can go. We have 0 potential energy. But then it's going to swing back up again. And once it reaches this highest point, we have the maximum potential energy. So we have 100%. All of that kinetic has been converted into potential energy. And when it reaches the top, it stops for an instant. And then right here, we have 0 kinetic energy. But at any time, these two have to add up to 100. These have to add up to 100. These have to add up to 100 because the total energy cannot change. Energy cannot be created or destroyed, only transferred from one form to another. So back to the two equations that we do know. And again, I've just written at the top here that we do have our total energy that I have as ET equal to the variables that they do show you on your data sheet, where it has the kinetic energy written as EK and the potential energy written as EP. So because the total always has to add up to the total, we can say that these two at some point are equivalent to each other. And we know the equations for EK and for EP, so then we can say that these are equal. So there might be a time where the height is 0, so there would be 0 potential energy, and it would be all kinetic energy. There might be a point where the velocity is 0, and then there would be 0 kinetic energy and 100% potential energy. And that's what we're going to take a look at. So always nice to have a picture, make it kind of visual. So what we see in this picture here is the girl standing on top of a ledge, and she's holding a ball. She's holding on to it. It's not moving, so it's kind of hard to see here. But there is potential energy. There is 0 movement. There is 0 kinetic energy, but there is some potential to do some work if she drops that ball. Right now, no work is being done, but as soon as she drops it, we do have the ability to do some work. So 100% potential, 0 kinetic energy. When she drops the ball, as the ball gets lower and lower, there is less and less potential energy. As she drops the ball, it's accelerating, it's going faster and faster, so there's more and more kinetic energy. So as the ball goes in this direction, the potential energy is going to go down. The kinetic energy is going to go up. Just before it strikes the ground is where it's going to have the maximum kinetic energy, and 0 potential energy because it is just about to strike the ground. So that in fact is the first question here. Calculate the velocity of the object just prior to striking the ground if the initial height is 14.4 meters. So just like all along, we're going to be showing graphs. We're going to show all of the information that we do have here. So let's write down what we know, which, well, isn't a lot. What we do have is a height. So our change in height, so we would use that for the potential energy equation, and that's equal to the 14.4 meters that we do have. So how can we go ahead with this and actually calculate the velocity? Well, let me just take this equation here and let me rewrite it. And actually, let me rewrite it with the 2 in the denominator. So mv squared. And again, for the v, we can sort of think of that as either velocity or speed. In this case, it is going down, so we can consider it to be a velocity divided by 2. And if we're saying that this is equal to mgh, so what I can do right away here is I can say, okay, well, it's like this is over 1. So if I take the right-hand side and divide it by mass, that cancels out. And then I have to do it on the left-hand side, divided by mass. Oh, and that actually cancels out as well. So nowhere in here are we given information about mass. And that's because you don't need information about mass because of what I just showed you. They actually go ahead and they cancel out. We'll also notice here that we have this lowercase g. So once again, you're not given this information, and that's because it's on your data sheet. Acceleration due to gravity, 9.81 meters per second squared. So that is our given information. Our required information is to go ahead and calculate the speed or velocity. 2 equations that we have here. So canceled the mass out. I no longer have the mass. And what I want to do now is I want to solve for the velocity. So I want to move this 2 to the other side. Again, different ways that you can do this. Here it's in the denominator. If I move it to the other side of the equal sign, it just ends up in the numerator. Let's tidy it up a little bit. So now I have v squared is equal to 2 times, oops, not the mass, we got rid of the mass, times gh, 2gh. How do I get rid of this square? Well, I take the square root. But if I do that on the left, I need to do that on the right as well. So now my speed or velocity is equal to the square root of 2gh. That is it. What do we have for our known information? Well, we have the height and we have acceleration due to gravity. As always, put in all your information 2 times with the units, 9.81 meters per second squared, multiplied by the height, which is our 14.4 meters. So we're going to multiply 2 times 9.81 times 14.4. Multiply those together, then we're going to take the square root of it. So maybe I better just show you all of those numbers multiplied together before I take the square root. So it is 282, and don't round anything until the end. 0.528. Keep all of those digits, then take the square root of it, and it works out to the correct number of significant digits. 3 is what we want to have. It works out to 16.8. It is meters per second. We are calculating the velocity. And yeah, so it is a velocity because it is going down, so we can give a direction. And we can say that it's actually down. All right, let's take a look at another one here. So here is, well, kind of like a pendulum, a swing that we do have going back and forth. So before we take a look at anything else, what is going on with the swing? Well, when the girl swings up and reaches up here, we have all, I'll put it as all, 100%. potential energy, and we have no kinetic energy. She actually stops temporarily at the top. When she's swinging back down, this is the lowest point right here. So because that is the lowest point, there is now going to be no potential energy and all kinetic energy. So very similar, we have an energy transformation that's going on here. So this is made a little bit more difficult because the lowest point is actually not the ground, but it's 0.5 meters above the ground. The highest point of her swing from the ground is 2.1 meters. So this is why it's useful to draw a picture, because what we're interested in is actually the distance here. That is the height. Remember, it is the change in height. So the change in height is equal to the 2.1 meters minus the 0.5 meters, which is equal to 1.6 meters. Okay, so picture is always nice. Make sure you realize what the lowest point is in terms of the calculating of your height that you do have. So we have our heights then, the numbers that were given here. What will be the velocity upon returning to the bottom? Okay, so we're starting with potential energy, and we want to convert that into kinetic energy, and then we're interested in what the velocity is going to be at the end. What else do we always know? Well, acceleration due to gravity, 9.81 meters per second squared, again, directly from your data sheet. What do we know? Well, eventually we're going to take all of the potential energy, and it's going to be converted into kinetic energy. So once again, we can write this. 1/2 mv squared is equal to mgh. We already saw the masses are going to cancel out. That's why we don't need them anywhere in here. And again, we're just going to rearrange it. In this case, it's actually to solve for the same thing, which is once again solving for velocity. So without going through all that work again, the only difficulty here is kind of realizing the two different heights that we have, and you're interested in the delta, the difference between them. So going back to that previous rearrangement, the speed is now going to be equal to the square root of 2gh. Taking those and plugging those numbers in, again showing all the work. And then divided by our height, which is the 1.6 meters. We do only have one significant digit here. So when you do plug these numbers into your calculator, take the square root, you do end up with 5.6028 and some other digits after that, meters per second, but we only want one significant digit. So because this is a 6, we're going to bump up the 5, and it works out to 6 meters per second for that. Okay, so that's our energy conversion going from potential to kinetic, but it could be kinetic to potential energy as well that you might need to solve for. So with any energy conversion, it will not be 100% efficient. So even if you think about the swing here, this girl swings up and then back in the opposite direction, and if she doesn't put any extra work into it, eventually she's going to get lower and lower and lower, and then after a period of time, she's not going to be moving anymore, and all that energy is going to be, well, it can't be lost. It had to go somewhere. Same thing with this pendulum. It doesn't continue to swing back and forth indefinitely. Eventually it will be less and less each time, and then no longer move anymore. So if energy can't be created or destroyed, well, why doesn't it reach the same height? And why do we not have the same velocity all the time? Well, eventually the energy is not lost, but useful energy is released, and it is released in the form of heat, and that is what the second law says. With any energy conversion, it will not be 100% efficient. Some energy will be released. Again, not lost, that's not really the right language. Useful energy, we could say, is lost. useful energy is lost, energy is released in the form of heat. And eventually, as in the case in the pendulum or the swing, all of that potential energy is gone, at least potential energy in terms of the height. All of the kinetic energy is gone in terms of the movement of the swing. It's been converted into the most disordered form of energy, which is heat. And what we also talk about is entropy. The entropy is going to continue to go up, and this is a measure of disorder, and the most disordered form of energy is going to be the heat energy. At any rate, what you need to know for this course is how to calculate the efficiency of it. So think about a vehicle, putting gasoline into the vehicle. That fuel that you put in has a certain input energy, but not all of that energy goes into moving the vehicle. A bunch of the energy is unfortunately going to be lost in the form of heat. So all you need to do is feel a running engine and you can tell that it is hot, and a lot of that energy is then lost in the form of heat. So this is the equation that is on your data sheet. And big thing, don't try and remember it, take a look at it. What students always flip around is the output and the input. It is output divided by input, not the other way around. Input is the amount of energy that initially goes in. Output is the amount of useful energy that is generated in order to go ahead and do some work. So let's take a look at a problem here. So for this one, what we do have is a motor that we have this amount of energy. So it could be an electric motor, and we're putting this much electrical energy into it. It could be a gasoline motor, and that much energy is going into it. And that energy, what it's going to do is it's going to result in some work being done. So taking a 30 kilogram mass and lifting it up to height of 2.4 meters above where it started in the first place. Okay, so what does this look like? We use some energy in order to take our mass and move it up against gravity, a height of 2.4 meters. So we've taken the energy that we put into the motor and used it to transfer it to potential energy. And this is now the mass that we have at the top here, which is the 30 kilograms. You needed to use some energy, you needed to do some work in order to do this, but unfortunately, some of the energy is going to be lost in the form of heat. So, how much energy, how much potential energy does the mass gain during the lift? So the first part here is just taking a look at, well, that equation for potential energy. So the EP is equal to mg delta H. What is our known information? Well, we already know that the mass is equal to 30 kilograms. We already know that the delta H is equal to 2.4 meters, and once again our acceleration due to gravity is the 9.81 meters per second squared. We have everything we need to use this equation. We don't even need to rearrange it. So we have our 30 kg multiplied by the 9.81 meters per second squared multiplied by the change in height, the 2.4 meters. Multiply all of those together, and what you do end up with is 706.32 joules, kilograms times meters per second squared, joules that we do have. So we do have our least precise number here, 2 sigdigs, but I'm not going to round this right now. If you were asked for the answer for this, you would round it to 2 sigdigs, but we're actually going to use this for a further calculation, and we're going to calculate the efficiency. So because of that, we're not going to round it at this point until our final calculation. Then we could round our answer. So efficiency, what is the equation for? I'll just put it here as this, efficiency. Remember, it is the output energy divided by the input energy, directly from your data sheet, times the 100%. Output. How much energy did we get out? Well, the energy that we got out was the energy that we got from raising this 30 kilograms up 2.4 meters. So this here is our output energy. Make sure you understand that and read it carefully. So at the top, output energy is the 706.328 units or joules. Input energy was the fuel or the electricity that we put in the first place, and that is the 1300 joules that we have up here. So that's where we're going to use this number. We're going to put in our 1300 joules. Joules cancel out, multiply by 100%, and that's going to be our unit, is percent. So when you plug these numbers in, what you do end up with is 54%. So what does that mean? Out of the energy that we put in, the 1300 joules, 54% of that, just slightly more than half, which is actually very efficient, went into lifting this mass. What happened to the other 48%? It was released as heat. So I say that this is quite efficient because if you consider something like a car is only about, well, typically 25 to 30% efficient.